Let's continue with our discussion of using the standard normal distribution. Whether you wish to open Excel and use the Excel commands, open your calculator and try and use the calculator distribution commands, or turn to Appendix C1 or C2 in the back of the book and use the tables, we're going to try and play around and do some more evaluation to figure out what's going on here. This is problem 29 out of the text. We have a liquid soap dispenser, and the average volume is 600 mils, and the standard deviation is 5 mils. And so now we want to look at, if we pick up a bottle, what is the chance that the amount of soap is greater than 592 milliliters? If I were to do this in Excel, there are two different ways I can do this. I can ask it to give me the normal distribution as a CDF. And the cumulative version would go from minus infinity up to 592. So if I draw the picture, the average is 600. The standard deviation is 5. I want to know what's the chance we're greater than 592. 592 is less than 600. I want this area. How do I find that? I have several different ways I can do that. Aha! Everything from here over is 50%. Great. So now what I need to find is that piece. What do I do, boss? What am I supposed to do to find that piece? Again, there are several different ways I can compute this, Nick. I can use the standard table. In order to use table Appendix C, where those tables are, I need standard values. That's Z instead of X. How do I get from X to Z? Careful. What's the formula for Z? Right, it's always X minus mu. And then I divide by, which is 5 in this case. So that's negative 8 over 5. That's negative 1.6.
It's negative because you're trying to find on the left.
It's negative since I'm on the left, but my table only deals with numbers that are on the right. But because of symmetry, the area on the right and the area on the left are the same. So if I know the area from my table that goes with a positive 1.6, I have this answer. And if we look at the top of the table in Appendix C, we see a picture that looks like this. And that's how I know that the table in Appendix C only gives me positive Z's. Yes, sir. Yes, in any distribution, the mean is in a normal distribution. The mean is in the middle like that. So I go to the table in the back of the book, table C1, I cheated and put a little bookmark on the edge of the page back there so I could find the appendices quickly. Appendix C. Four, 5, 2. So what's this total chance? Wait a second. I didn't quite hear what you said. Say it again. 9, 4, 5, 2. I have to add these two together to get my total shaded area. Now, here are two other options. If I'm in Excel, the cumulative distribution starts all the way on the left and works up to a number. So I could say what I really want is to start all the way on the left and get to negative 1.6. That wouldn't give me the shaded area. That would give me the unshaded area, right? Take a look at table C2, which we didn't do very much of on Wednesday, but the picture at the top of table C2 is a left tail. That's how I know this is a cumulative version rather than the PDF. This is the CDF. So if here I use negative, notice there are negatives in this version of the table. I could use negative 1.6. And if I do that, I get 0.0548. But that's not my answer, is it? Why not? I'm sorry, I heard somebody muttering over here. I have to subtract from 1 because that's the unshaded area. And with a CDF, we get probability of X being less than something. And so this is our 0.0548, which is 9452. In Excel, the CDF command normal distribution. I'm looking up the number 592, where the average is 600, the standard deviation is 5, and I want a cumulative distribution. So there's a command right there in Excel to give you this 0.0548 directly. Questions? Yes, sir. Absolutely. So on the calculator, when I'm doing the normal cumulative, all of the calculator versions are under the distribution menu. The distribution menu is right here above the word variables. It says DISTR, distribution. So I hit second variables button to get the distributions. And I want the normal CDF. That's option 2. Now I'm pretty sure that we get this menu. And if you don't get this menu, then you don't have the right version of the operating system. And you can upgrade that on the calculator on the TI website if you really need to. But if you don't have that, we can look up the manual. I'm going from all the way on the left, negative infinity as far as the calculator is concerned, up to where? Where did I stop? Where was my line drawn from the left up to? Negative 1.6, right? But I could also do this version, couldn't I? Because it lets me put in the mean and the standard deviation. So I could say, oh, I want to go up to 592, where the mean is 600, and the standard deviation is 5. So notice here, Grant, that I don't actually have to use the standardized versions on the calculator. I could, if I left the mean at 0 and the standard at 1, I could use the z-score instead. Notice that the bottom command says paste. So when I hit enter, it throws up the command, and then I have to hit enter again. 0.0548 if I round. And then I want 1 minus that number, 0.9452. If I did it in the standardized forms, distribution, normal CDF, negative 1.6 with an average of 0 and a standard deviation of 1, because that's what standardizing my data does, is it changes the average to be 0 and the standard deviation to be 1. I get that exact same number. But if that's this one right here. To negative 1.6. And you're right. If I did the whole thing to positive 1.6, that would be the mirror image of this picture, wouldn't it? And that would give me the same answer as this. And that's part of why I like the drawing. Because if we take the picture we had up at the top there and we turn it around, isn't that the same picture just flipped over left to right? So that would be the area 0.9452, I think. Let's check. Well, lo and behold, that would be changing this from negative 1.6 to positive 1.6. Ta-da! So here's my problem. And it's not a big problem, it's a small problem. There are like 8 different correct ways to get this answer. Which one are you going to use? I don't know. But to that end, I need you to write down what you're doing in your Excel file or in your calculator or in your table lookup so I know where the number you got came from. Not just that you have the right answer, but that you showed me that this is how I got the right answer. And a bunch of you saw that on the homework I just gave back. I've got the word how written in a bunch of places. And in some of the cases, it was, you gave me a number that the number you gave was correct, but it doesn't answer the question I asked. It answered a different question. Like in a couple of cases, the one about the modems in the car, you had to have at least 8 working modems. If you did the probability of being equal to 8, that's the chance you have exactly 8 working modems. But you could have had 9 working modems and it would still be fine. You could have 10 working modems. So really, in order to do that problem, you need to add 3 numbers together, or you needed to use the cumulative version of the distribution, all of which are available on these tables. Take a look at the key on our Canvas page. But if you draw this picture, then I should have a better idea of where you got started. And the same thing holds true in the discrete case. If you were to draw the histogram and shade in the bars we wanted. Most of the time when I am working with a normal distribution, we write n mu sigma, where mu is our mean and sigma is our standard deviation. And that means that my standard normal curve is written n01. That way I don't have to write out that big crazy ass equation that we were looking at the beginning of class on Monday with the e and the 1 over the square root. Now, the hell with that. I don't need it. But that means I can tell you, hey, I've got a problem that uses this normal distribution. As a matter of fact, I'm once again stealing a problem from the textbook. You're going to love this one, Anna. On January 2011, a new standard for baseball bat liveliness called the ball bat coefficient of restitution, how springy is your baseball bat when you swing it, was adopted for teams playing under NCAA rules. A higher coefficient allows the ball to travel further when manufacturers want a high ratio, but the maximum allowable one is 0.5. Big Bash Incorporated produces bats whose coefficient of restitution meets this normal distribution. What is the chance that you get a bat that exceeds the standard? And we just said that the maximum allowable coefficient is 0.5. So this question says, what is the chance that you get a bat whose coefficient is too large? Now they actually say, what is the percentage of bats that this company produces that exceed the standard? Think about it. If you want to do business with Big Bash Bat Incorporated, do you want that to be a high percentage? No, because then you can't take those baseball bats and sell them to your NCAA teams. You have to trash them or sell them on some other market, right? But all of a sudden, you've got a whole bunch of stuff you can't use for the contract you've signed. Is that this is a high percentage? That's a problem. How do I get this number? First thing you should do is draw me a picture. I wonder if that's something you could and then find out what the coefficient of restitution for this one is. It doesn't say right here on the side, which is a shame. What's your picture look like? What part of it is shaded? What numbers are where?
That's the mean. Right, I have 25. And everything to the left is shaded, or to the right.
I was going to say, yeah, I actually want this stuff over here, right? I want to know what percentage exceeds the standard. How much is too big? And now you have all these different ways to go about getting it. So how are we going to come up with that area? I'm sorry? That would be true if it was a rectangle, but it isn't. It's that funny tail of the curve. So when I actually come to getting the area, that's the calculus part. We're not going to do that. We're going to use the tables or Excel or the calculator somehow. I just want to know what calculation you're going to do. Get it? I'm going to make an executive decision. I want to use the table. If I want to use the table, what do I have to do first? I have to find a z-score. I have to standardize my data like Nick had suggested earlier. So if I'm going to use the table, I need a z. Talk me through your calculation. Over, but the standard deviation for this distribution is this number. So I'm not dividing by 1, I'm dividing by 0.008. And I realized that when you said that, we even have another issue. What's the top is reversed, right? The mean should come at the end. Oops, let's flip those. Z is 0.5 minus 0.48 over 0.008. So I'll give you the 0.2 up there, but then I'm dividing by 0.008, and that is 2.5. 0.02. Helps if I write down the correct thing that I say. Okay, now I have the z value. If I'm using the tables, you have two choices. You want to use table 1 or table 2? By hand. Which table do you want to use? Table 1. If I use table C1, the picture at the top of table C1 shows me this, right? So if I go to 2.5 on this table, I'm not going to get exactly the number I want, because what I want is the tip, the tail here, and this is going to give me the area next to the tail. So I go to 2.5, and I get 0.4938. But notice my problem is that the part of the picture that table C1 shades is not the part of my thing that I shade. How do I get the number I want from this number? I got to subtract it? Oh, careful. I'm only looking at this part of the graph. It's 0.5, not 1. This is half the picture, so that's half the area. Half here is 1/2, 0.5. So the tip that I want is actually 0.5 minus 4938, which is 0.0062. Which makes me really happy because that means less than 1% of the bats they make will fail my test. That's good. 99.4% of the bats they make I can sell to NCAA teams. Talk to me, Michaela. That's good. Okay, I'm looking at the shaded area here versus the shaded area I want. This is what that table gives me, but I want this. Up there, you see how this part's not shaded? This is not the part I want, but that's the part this table gave me. I want the rest of it. That's what's missing. So I have to subtract from something. How do I know what the something is? Well, I look at this picture. And this picture is only half the curve, right? The whole area is 1, so half of the curve must be a half. And that's only because I know this picture is symmetric left to right. You're still looking at me funny, Katie. Talk to me.
No, I was just confused why you subtracted 3.5.
Okay, it's always a matter of what did the table give me and what do I actually want. But I only used table 1 because Kirsten suggested it. What if I use table 2? Table 2's picture Table's 2 picture looks like this. And that's the cumulative distribution. It's starting from all the way over on the left and going to the line. So if I use that same z as 2.5, it'll give me all of this on table C2. And so let me pull up table C2 and we'll look for the number 2.5. See how the picture looks? How it's going all the way over from the left? 2.5 is way down here, 0.9938. But that's, Katie, this is the same situation. That picture is not the area I want. I don't want the left side of the line. I want the right side of the line. So if I've got the whole picture, I then take away this number from what? From 1. The best part is that it doesn't matter which version I use. And again, Grant, I could do these on the calculator. We already know the commands to get this version with the CDF, right? So I can get this calculation right off my calculator either way. Again, assuming you like and are willing to work with that calculator. If I'm going to have you do this crap on the exam, I'm going to give you these tables as well. I'm not going to require you to memorize all these new tricks on your calculator. Homeworks and stuff, use Excel, use the calculator, use the table. Just tell me what you are doing. Questions?
On the exam, would you have the standard deviation?
I have to somewhere, otherwise I don't know how to standardize my data, right? Or I better assume that you have that information somewhere in the problem. We can't do this without it. We will, moving forward from here, ask where did those numbers come from? Did I pull them out of my ass? Did we make them up? Or did we somehow look at the population and deduce what they should be? And we'll talk about how to get those numbers, but that's later. We can actually use this to go backwards. When we were doing descriptive statistics, we talked about taking the mean of our numbers and using all of them, and then we talked about a trimmed mean, right? We said, don't worry about the top one or the bottom one, or the top 5% or the bottom 5%. If I know that I have a normally distributed population, then I can ask about what values are the cutoffs for the top however many percent. This sounds very vacuous. Let me nail this down to an exact example. Let's do weight. Weight is normally distributed. Now, I am going to make some numbers up out of thin air because I do not have a nutrition and dietetics person in the room to tell me about averages and standard deviations for weights, so I'm making crap up. Suppose for a 6-foot adult male, weight is distributed normally with a mean of 175 pounds and a standard deviation of 15 pounds. I didn't say anything about health standards, right? So, when we were dealing with descriptive statistics, we did things like quartiles. Where are the 25% marks? And we talked about the middle 50%. I would like to know the middle 50% weight range. I expect half of the people who come to this doctor's office to be weighed to be between what and what. I'm sorry, half of the adult males who come to be weighed to be between what and what. First thing I'm going to do is draw a picture. Now, here's the weird part about this. I want the middle 50%, right? What part of this graph should I shade in to see the middle 50%? Nick? Aha, but 25% of the area, right? And given that this area is small on the right and small on the left and big in the middle, I would expect a number to be closer to the middle rather than further away, to be 25%. So I could say, hey, wait a minute, what I really want is this area to be 0.25. And I want this area over here to be 0.25. Now, I don't know what those numbers are. I don't know where the cuts should be made. Oh, crap. How do I figure out these? Where to put those lines? I can work with my standard normal distribution. So I'll write this. This is N01. So I'm working with Z at the moment, not X. But that means I can look up the number whose area is closest to 0.25. Turn to table C1. Because that picture right there at the top goes from the middle to some number, and I can find the shaded area. I want the area number that is closest to 0.25. Say it again. 0.0987. That is what I get when I put in 0.25. I want the number in here that's closest to 0.25, and then I need to figure out what the Z is. Nick? Aha, 0.67 gives me 2486. 0.68 gives me 2517. So it should be in the middle between those two, right? We can use 0.67, we can use 0.68, or we could split the difference and say 675. As a matter of fact, in our section, I ate it. What page is that on? This is what happens when I don't look at the textbook to tell me what page stuff is on. Page 245. It has this list right here. And it says, oh, the middle 50% should have a Z of 675. But now I know on here that this Z should be 0.675. What's that one? Oh, I'm going to write Z next to that so I remember that's a Z score. What about the left one? Just negative, because it's the same on the left as it is on the right. Now those are Z. But the question's about weight, yes? So I need X's. I don't have X, I have Z. What's my equation that helps me go from X to Z? Same equation, I can use it now here. Z is X minus the mean over the standard deviation. Only this time, instead of putting in X to get Z out, I put in Z to get X out. So, you want to do the negative or the positive? I'll start with the positive one. If Z is 0.675, that's X minus the average over the standard deviation. Because I got those numbers from right here. Mu, sigma. Great, now I can work out what x is. Multiply the 15 over x, 0.675 times 15 is x minus 175. Somebody give me that number. Add the 175 over, and I get 185.125. Now that's the high end. That was the positive z value, so that's the upper end. Where's the lower end? I'm going to do the same calculation, only I'm going to use this z value. And that means the only thing that changes is the left side of this part of the equation has a negative on it. Everything else gets carried through exactly the same way. This time it's a negative 10.125. So when I add the 175 on the other side, what do I get? Say again? I think you made a subtraction error. 164.875. Because when I said I've got to subtract 10, that'll give me 165. I got to go down another quarter. Arithmetic. We have calculators, I promise. Don't do it in your head. But now I can say, oh, 50% of the adult males that come to this practice should weigh between 164.875 pounds and 185.125 pounds. Okay. This does not fit that description. The last time I asked a problem about this, instead of using adult males, I actually used fetal weights, newborn babies. And I said at 6 months old, a newborn baby is considered undernourished if they are 3 standard deviations below. And so I asked, oh, well, what weight is that? These are adult human males. Let's consider somebody morbidly obese if they are 3 standard deviations or more above the mean. Notice this doesn't actually ask me any question about an area. It just asks me what x goes with the z, right? The z-score in this case is 3. And I want that to be put into this standard format. Now remember, I made these numbers up out of thin air, so I have no idea if this is accurate or not. I would say it's probably not accurate since I made this crap up. But if this were correct, then that cutoff weight would be 220 pounds. I'm pretty sure I made stuff up this way wrong, but there you go. we could say, all right, what about the top 5% of people, the bottom 5% of people? Maybe we're doing GPAs, right? If I assume that GPA is normally distributed, which is in and of itself a big assumption, I could ask, well, what are the top 5% of GPAs here? I could ask, what are the top 5% of incomes, assuming income is normally distributed? Now, I know for a fact neither of those pieces of data is normally distributed. So that's a horrible thing to do. Why is GPA not normally distributed? Because there's a hard upper number. You can't get anything above a 4.0 here. The same reason I know that salaries are not normally distributed is because that upper limit can go off to a hell of a lot bigger, and I don't want to compete with Jeff Bezos for salary. Questions? On page 245, that list going back and forth, a couple of these numbers we're going to use a lot. We're going to use this 95 and 98 and 99, and we're going to use this 90 a lot. So 1645, 196, and 2576. Those are numbers we use a lot. It turns out that there are lots and lots and lots of different normally distributed variables. And there are lots and lots and lots of not normally distributed variables. So why am I really focusing on normal? Why am I making such a big deal about this one if there are so many other options? By the way, if you look at the rest of chapter 7, which we are not going to do, this book contains at least 3 others. We're just not going to use them. Why? Because I'm a lazy SOB. No. Well, yes, but no. Because what we're really going to look at is the other side of the coin. And that's what we started with, and that's sampling. When I take samples from a population and I do statistics, well, turns out that the more I do sampling, my samples look normal. Even if the underlying probability isn't normal, sampling is normal. And we use sampling to test things. And that's next. But that's chapter 8, and that means we've finished chapter 7, and that means 2 class periods from now, you have a homework assignment to do. That's Monday. That's chapters 5, 6, and 7, and that's a lot of very massive chapters, which means we're having an exam. That exam is 1 week from today. We'll see you all on Friday. I hope you have a wonderful rest of your day.